Thank you very much. That was a fantastic introduction. So I'm Mieszko. Yeah. Well, have a look at the chip. Play with it. That's really the key here. So I'm Mieszko, and I'll be talking about this chip and the technique that we developed and tested in this chip. And this is joint work with all these people. The top 3 people, including myself, built the actual chip. I did most of the chip design, and the 2 gentlemen helped with the back end and designed small pieces in the chip. And Srini Devadas is my thesis advisor. So you can build a 1,000-core chip today, no problem. So the chip that I passed around has 110 cores, but really, if you give me 10 times the area, I will give you 10 times the cores, and that is not, it's definitely feasible. But the problem is, how are you going to program it, and what are you going to do about shared memory? And the 2 traditional approaches are to make a system with cache coherence. You have lots of small caches that are kept coherent by a complicated protocol, and they have these directories which can be large and take up a lot of space. And the other approach, which Nikos among other people has worked on, is to basically divide the cache into small pieces and have each piece of data cached in a specific location. The problem is that it requires careful data placement, and it requires round trips for any access to remote cache to keep the coherency model. And we'd like to suggest a new way of doing this, an alternative mechanism, which we call execution migration. And in the rest of the talk, I'll talk about why thread migration in hardware makes sense, what we need to build it in terms of architecture. I'll talk a little bit about the chip, and I will talk about how this particular chip has allowed us to reduce design complexity and how well it performs compared to basically the state of the art. So how is this done today? In a typical CPU, you have these first level caches, let's call them L1, and last level caches, let's call them L2 for argument's sake. And the fast small caches are private, typically, and the last level or next level caches tend to be sharded all the way across the chip and split into little pieces that are close to the various cores. And generally, when you're running a thread on a core, then the data is fetched to the thread. So when you're running the thread on core 1 over there, you're generally accessing its own cache. But when the cache capacity is exceeded, you have to access the various pieces of data that are cached in different places. You can move some of it around, as people have done with Arnuka, for example. But really, the key is that locality is really, really important in these systems. Because if you can turn these remote L2 slice accesses into local accesses, then you can win big time, right? Because you don't have to, especially in a chip that has, that's fairly large, has hundreds of cores, then the distances become very large, and the delays of accessing this data is pretty are pretty long. And so our idea is to actually move the threads around. So instead of moving the data, fetching the data to the computing thread, we're just going to move the thread around to bring it closer to the data. And the intuition there is that often the actual computation, the computing thread, the description of the computation you're doing at the moment, is much smaller than the data that you're doing the computation on. And effectively, we use this migration to exploit data locality by basically obviating the need for directories in our design, and making we believe, a pretty simple solution that's easy to prove correct. So the problem is that it requires an efficient hardware solution, because if you use the kind of thread migration that people do today at operating system level, there's just no way you can amortize the cost of moving the threads around. There's just no way you're going to have enough data locality in a program. So if we were going to build this in hardware, what would we like? We would like the migration to be fast. So specifically, we decided that it should not involve the operating system or any kind of software because it's just too slow. You cannot amortize locality. There's not enough locality in a computation to amortize slow migrations, and should not involve round trips. Like in cache coherence, you basically have to do a redirection through a directory and whatnot. So we try to get rid of that as well. If you're going to use this frequently, then you need to have these migrations at a fine grain. That is to say, because data access patterns change very quickly at sort of basically at instruction level, the system needs to respond at instruction granularity to really take advantage of these small variations in data locality. And again, this argues for not only hardware, but also the lack of any centralized scheduling. Yes, sir?
What about the compiler or runtime?
Well, we'd like to, so in this case, we don't have any specialized runtime.
Okay.
This is basically bare hardware, bare metal. There's
right, I'm just wondering, what about involving the compiler or the runtime system in these decisions?
So it depends on what granularity you're asking the question, right? So I will show in the next few slides what kind of sort of locality we're hoping to take advantage of.
Okay.
And in this case, I don't think that the software can respond quickly enough. Basically, by the time you've tried to exploit the locality, it's already over. I think in terms of program phases, then yes, there is definitely a place for the runtime system and the compiler, and more specifically, in terms of data placement. This is a problem that we haven't really addressed in this project. But this kind of architecture is very sensitive to where the data is cached. So that's something that Nikos, for example, has looked at in the past. Right. So finally, we'd like this to not take too much power. So we'd like the migrations to be as small as possible. And this was a design goal in our chip to only migrate a useful subset of the actual computation. So in principle, how would you migrate threads? In principle, if you look at this sort of block diagram of a chip, well, you have some kind of register file which has the running context, as the registers, the PC, and flags and whatnot else. And roughly speaking, you basically have to take this. You have to serialize it onto the network, put it on the interconnect, and the interconnect will somehow deliver it to the other core, wherever it might be. You slap an address on it, and at the destination core, on the right-hand side, you basically undo this packing and load the context into the running core. So in principle, it's simple, but let's look at what requirements, what actual architectural problems arise from this. So one question is, how are you going to do this migration? When you're going to decide how to migrate, and what are you going to do with any thread that is currently running there? So here's a pretty sort of the obvious way to do this, but not necessarily the best way. So in this case, we're just going to say that if a blue thread wants to migrate to the red, to where the thread is to the red thread is currently running, it's just going to go there and kick out the red thread, which is going to go where the blue thread used to be. The advantage of this is that the thread you just kicked out is likely to find a resource because, well, you just left a core empty, effectively, or at least a slot available at a core. And if it goes back there, then it's likely that that slot is still unoccupied. The problem with this is that well, this can cause deadlock, basically because you can have, for network indirections, you can have a loop where, with several of these, and the evictions can be blocked by forward migrations, and then the system locks up and never makes any progress. So in effect, to prevent deadlock, you need some sort of escape mechanism. And the one we chose for this is we chose to replicate the thread context in our course. And so we replicate the register file, the program counter, and we have the same pipeline. It's it's sort of like simultaneous multi-threading. So each core has a native context and a guest context, and the native context can only run the thread that was originally born on it, in a sense. And the guest context is for all the other threads that come and want to run on your core. And the reason this works is because when you are evicted by another thread, then you always go to your native context where you are always guaranteed to be accepted, because nobody else basically can run on that native context. So that's the deadlock escape mechanism. So on the other hand, if you're doing any kind of migration, for example, if two threads want to migrate to different places, you can just go there whenever you want to, regardless of whether that is your home core or not, whether that is your native core or not. If, however, you have this situation again where you want to migrate to a core where another thread is running, you kick that guy out, and he has to come back to his native core. And that allows us to basically provably avoid deadlock, provided you have either two networks or two virtual channels. And also we can prove that there's no live lock in the system, provided that if you migrate to a different core, then you at least make some progress, at least do one memory access that you basically came there to do. then the whole system makes progress. Yes, sir.
So is one of your, so you're using two virtual channels, is one of those a dedicated escape channel?
One of them is dedicated. So one of them is dedicated to these evictions, right? When you kick a thread out, then it uses that virtual channel, and that ensures that forward migrations, as it were, migrations which basically migrate because they want to access data, they never block this guy trying to get back to his home core.
So theoretically, if there was a core into which a migration decision was never made, that core was never selected to have anybody migrated into, then that one slot that this core keeps available would be always not used.
If you never have a thread that was born there, then then you can waste that. You can basically power down that core. I mean, it seems a lot worse.
You can power it down, so but you're underutilizing it, the parallelism wise, but also at least you can not waste energy by powering it down and kind of keeping it asleep.
Yeah. So in this chip that I passed around, there's no power down or power gating. There's clock gating. Conceptually, you can do this, obviously, right? So, but in some sense, we have this problem in architecture where we have all this area, but we can't power it all at the same time, right? I mean, this is dark silicon business, and well, what are you going to do with all this dark silicon anyway, right? So, so as long as you can keep it off when you don't need to use it, I think it's reasonable to use extra hardware. Anyhow, so how do you do a memory access in this system? Well, you want to do a memory access, and say you're running in core A, and the first thing you need to decide is whether the address that you are accessing is cacheable in core A, based on this NUCA principle. And if it is, then you're done. Basically, you can access your local cache and continue executing. If it is not, then you migrate to the home core, that is to say the core that can actually cache this address that you're interested in. Then, as we saw, you have to see if the number of threads that can be running on this core is exceeded. And if it's not, then again, you can just access memory locally there and continue running. And if it has been exceeded, then you migrate, you basically kick out the guy who was already there, or if there aren't enough slots, and he has to go back to his native core to prevent deadlock. So how does this do? Well, the problem with this kind of system is that it has very high migration rates. Yes, sir.
So could you go one slide?
Yeah.
What happens if the thread that's already there is like if that's its native core?
So the guest, that core has two contexts. Remember, the native context and the guest context. And the native context is reserved for the native thread or for its own threads.
Yeah.
So when you migrate, you are only allowed to use this guest context. So this case never arises where you kick out the guy whose home is there, basically, because he's guaranteed a space. Yes.
Can you have thrashing of the guest contexts?
You can, and this happens to some extent. And I will show some of this in the results section. Yeah, there's a specific case. basically, if you oversubscribe, if you have, for example, if you have 100 cores and you have 100 threads running, basically by the birthday paradox principle, you will get some that want to contend for the same core. And if you're not careful about scheduling it a little bit, then you can get crashing, which can limit your performance. So this shared memory system, based on just migrating threads, it has the problem that you migrate too often, basically, right? So this is a high-level simulation using a set of benchmarks, and we see migration rates for in some cases for 90% of the memory accesses, right? Which means that that nearly every memory access goes to a different core, and that becomes expensive because the migration is expensive if you're not going to amortize it. So the question becomes, do all of these migrations that we're doing, do all of them exploit actually some data locality? And it turns out that many of them don't. Many of them are just one-off. So this shows the number of contiguous memory accesses to the same slice of cache, and this shows the number of memory accesses in the benchmark total. So a lot of these accesses just go to a different core, go through all this migration trouble, just to retrieve or write one piece of data, and then they go back or go somewhere else. So to amortize the cost of the migration, we'd like to make a trip for only more than one reason. That is to say, if you're going to access several pieces of data at that core, then it's worth making the trip. And if you're not, then it's not, right? So in the extreme case over there, you can get a pretty long stretches of contiguous accesses, but in most of these benchmarks, there's a small number between maybe 4 and 10 contiguous accesses that we have to work with. And yes.
I'm sorry, what is 56 the magical number? What's the reason?
The magical number is 4. So so 50.
I thought it
You
was
mean,
7.
so no, it just happened that so basically we picked a bunch of benchmarks, these benchmarks, which are mostly Splash, and we ran them in a high level architectural simulator, and we counted the number of times they access a particular memory range, right? And it just so happened that one of them just exhibits this high locality, but most of them don't. Most of them are sort of in this range. And this is really the answer to the question that was asked earlier about do you want to involve the runtime system and software in this? And the answer is that you can maybe amortize if you're on that end of the scale, but there's no way you can amortize this kind of fine-grained locality changes in software. Yes.
Do you address interleave the data?
Sorry?
Do you address interleave the data among the cores?
No, so we took the entire address range and we split it among all the cores.
But interleaved or blocked?
Blocked.
Blocked.
Yes. Yeah. So we tried different things, and we didn't spend a huge amount of time optimizing the data placement and interleaving. And also these benchmarks that we ran, they were off-the-shelf benchmarks and were optimized for cache coherence, right? So for example, they don't do things like write, basically do full sharing, right? Write the 2 different pieces of data in the same cache line in 2 different cores. So they're optimized for this kind of level, but they're not optimized for migration. So if you do that, then you can possibly do better. So yeah, so we'd only try to. Yes, sorry.
So just for the case where you're only hitting the one remote data element, is that by any chance a lock, like a spin lock acquisition?
In this case, it is not.
It is not.
Yeah.
Okay.
So if it were just locks, it would be easy, right? Because I could say, oh, these are just locks, and we have a special piece of hardware for this. No, problem solved. No. So this actually happens fairly often. And I think actually there's a lot of room for compiler and RTS level optimization to prevent this, because if you think about how memory allocation currently works, is you do a malloc and you get basically the next slice on the free list, right? Wherever it happens to be. And in a system which is sensitive to where you actually can cache the data versus where your thread is running, you'd like to be able to have some more control, right? So for example, you might have a malloc that says, oh, I want to allocate this much data, but it should be near this other this other pointer that I pass it,
So
right?
it's a lot like NUMO where memory allocation, except on steroids.
Exactly, except it's at a low level, right? So,
Okay.
um, so I think clever compiler and RTS work can reduce some of this, because a lot of this I think has to do with the fact that basically compilers don't care because they get this for free from cache coherence. Yes.
So this is for ocean from cluster,
Yes.
contiguous along the limit.
We have, yeah, we
You
tried
have
both.
both there, but which one is the? You have both contiguous and non-contiguous, but which one is that?
I think that is ocean contiguous. I wouldn't bet my right hand on it, but I believe it is. So anyway, so we'd like to turn these one-off accesses into actual one-off accesses, have some cheaper way of making these, executing these accesses. And so we're going to modify our memory access system in this way. We're going to start as we did before. If it's cacheable in the core that you're running in, then you're done. If it's not, then you can either choose a remote load store operation, that is to say, basically the hardware sends a message to the remote core. The remote core basically executes the load or store or whatever on behalf of the original core, and sends a message back with saying here's the load result, and continues execution. Alternatively, if you think you might have enough data locality, then you're going to migrate to the home core as before, and continue execution there. And possibly kick out somebody else who's running there. The key here is this decision, and I will talk about how we ended up implementing it. But this decision, as you can see, is key and you want to detect how much locality you're likely to have. That is to say, only migrate if you have several consecutive accesses. Another question is, well, if you're going to do this migration of this thread context, how much of this thread context should you migrate, right? And so we did some experiments. Out of 16 architecture registers, this is x86 64, in most cases, only very few are used once you make a migration, right? So you migrate somewhere, you read or write maybe 3 or 4 registers out of the 16, and then you come back. So the obvious solution is you should only take the registers that you're actually going to use, as opposed to taking all this junk that you're never going to access. So our sort of trick solution to this, in this particular chip implementation, has been to just implement a stack machine architecture instead. And the advantage here is that if you're going to migrate a part of the context, then you need to only choose one number. That is to say, how many stack entries you're going to migrate. And you're going to only migrate the program counter and the top of the data stack. And basically, it's sort of an underhanded trick, because we've moved the problem of choosing which piece of data to migrate up to the compiler, right? Because the compiler will effectively keep the most used data on top of the stack. Now we've done some work that I won't talk about here on basically we've shown that you can do this in a register architecture. Basically, it's kind of like you can think of it as a fancy LRU system. You can sort of predict which registers are going to be used. But this is actually what we ended up implementing in the chip. So the chip itself, it's somewhere here being passed around. I don't know if you can see very well, but this thing on the right is the chip. It's just the lighting that it looks kind of rainbowy. It's basically a piece of copper on top, right? So it looks kind of golden and shiny. And this is the chip that's sitting in the socket in its package. So the chip is a 110 core processor. So these cores are sort of the custom, as you saw. These are the stock architecture cores. Nevertheless, this is the largest such chip that has been built in terms of core count. That is to say, any chips that have more cores on them that generally don't support shared memory. It doesn't have automatic data replication, so it doesn't have cache coherence per se. It basically uses the system, this migration and remote access combination to support shared memory, the shared memory abstraction. And it's general purpose, unlike, for example, a GPU, which can have many small cores, but you have to program it in a certain way. This, you can run your C program, and it will actually, it will do what you expect. You don't have to do some funny CUDA stuff. And yeah, you might have to optimize it in a different way if you're interested in performance. But the first time you write a program, you run it and it works, and you get the right answer, and then you start optimizing. And the key contribution of this chip is that it implements this thread migration that is very quick and autonomous in hardware. And in fact, there's no RTS or software involvement. And it's the hardware that decides when it should migrate, and I will show how we do that. And it supports partial context migration in the way that I described. When you want to move a thread, you only move the portion that you expect will be used remotely. As an effect, we significantly reduce interconnect traffic on some of the benchmarks, because basically, instead of moving the data to where the computation is, which often is a lot more data, depending on the computation you're doing, you're moving the computation, which is often smaller, to the data, and making sure you amortize that over time. So the chip itself is 1 square centimeter. It's in 45 nanometer technology. It's not the absolute cutting edge. I guess that would be 22 nanometers. So maybe it's 2 generations back, but it's still pretty. I think it's still pretty challenging. It has 357 billion transistors, roughly speaking, which is basically average density for a chip of this size these days in this technology. It's laid out as a 2D mesh, and it has a 2D mesh interconnect. It basically the standard network on chip router, a very simple thing, and it has 2 off-chip memory interfaces that are board off chip, and we're just bringing it up now. I literally got this board back and the packaged chips maybe 2 weeks back, and so I'm working on bringing this up. One interesting thing is that it took us only 18 months to actually design and tape out this chip, which I don't know if you're familiar with industry and generally how long this takes, but a chip of this complexity I would expect a year with a much larger team than this. So this was myself and 2 other graduate students at MIT. And the funny thing is, none of us knew how to build an ASIC before, right? So we could build RTL, we could write RTL, build hardware, simulate it, maybe push the synthesis button, but we had no idea what was what we were getting ourselves into, which was probably good actually. So what's in this chip? So as I mentioned, there are 110 homogeneous cores. We're hoping originally to have 121, but they basically didn't fit. In the backend process, it makes everything bigger than you expect, and each slice is the same, so they're all homogeneous. It has 32 kilobytes data cache and 8 kilobytes instruction cache, and there's only a single level of cache in this design. We're basically interested in seeing how this migration can manage this data movement, and for this we only need 1 level of cache. There are 6 on-chip network routers. We could have easily gotten away with 4. But basically, these routers are so small, and compared to the rest of the tile, that it was just simpler to just put 2 more routers on the chip. And because the interconnect is neighbor to neighbor, it's a mesh. You have so much bandwidth that there's no point in trying to optimize for reduced bandwidth, because you have all these wires. What are you going to do with them anyway? And it's a very easy way to ensure deadlock freedom for us. I mentioned that it's a custom-based architecture based on a stack. It has actually 2 stacks, which are basically run in an SMT context. So either one or the other is being run. So how do we actually do? So the minimum migration delay is 4 cycles. And this is compared to like milliseconds if you do it in an operating system and software. So this is really several levels of magnitude faster. And the way this works is the first cycle you begin to unload the context, and this is all pipelined, right? So if you have a large context, it doesn't multiply, it just adds. So you start unloading the context, you basically have a packet header with the destination address, and you load the PC in there, and then you have to travel across the network, which in the minimum case is just right next to you, and the maximum case of our chip is is on the other end of the chip. So this H differs depending on how far you are and what kind of congestion you have on the way.
The edges are not connected, right? So
It's not, yeah, it's not a torus, it's just a mesh, right? So if you want to get from this corner to this corner, you have to go this way or whatever. So you have to actually, there's no fancy this.
There is the flat mesh, and are you using concentration, are you using express links?
I'm sorry?
Are you using concentration or express links?
No, it is just a flat mesh.
Okay. 10 by 11.
It's 10 by 11 exactly.
Okay.
And there's routers on one hop minimum if there's no congestion.
Does this machine have paging?
It does not. It has no virtual memory.
Okay, so you're not bringing the TLB state with you.
We are not, but I think
What would
that
happen
it's
if you had to?
yeah. So this is a good question. The other related question, somewhat, right, is what do you do with the instruction cache, right? So do you need to bring up part of the instruction cache?
Yeah.
And we ran some experiments on this, and we found that basically you don't. So in the case of the instruction cache, for example, if you don't bring your instruction cache with you, then your instruction cache miss rate is higher by 7%. That is to say, if you're from 0.001%, you get 0.001007% misses in your system. So basically, it is not worth doing anything about it. Yes,
But isn't this highly application dependent?
it is, right? So
Because for the applications that you have here, the instruction string is so small that basically it fits in your cache. So
It
chances
fits in
are
the
that
cache.
after a few migrations, everybody has pretty much all the instructions in it.
exactly.
Other applications won't behave like that.
Well, so it depends on the application what you want to do, right? So some applications, but in effect, what you're saying is that some applications will require a slightly larger instruction cache.
Not slightly, in the terms of megabytes. If you look at database systems, the OLTP has a working set of instructions. The neighborhood is 1.5 megabytes. Working set, not the full print. Full print is 4.
So what we have found here, in at least in our experiments, which as you pointed out have been sort of limited to fairly small benchmarks, but nevertheless what we have found out is that instructions tend to be cached in different places because they tend to access different pieces of data, right? So the instructions that access a particular data region tend to be correlated and be living in the cache where, in the instruction cache, where that data lives, right? So they're sort of stuck together. So I'm guessing this is not the case for all possible applications, right? Because you can, for example, write a simple loop that goes through everything, right? And then you will have to replicate it. But I think in general, you can get away with having a slightly larger iCache. I would not expect to have 110 times the instruction cache, basically because of this effect, where the instructions that operate on a specific piece of data, they tend to go where that data is. And yeah, the first time around you have a miss, but the next time you go there and execute the same piece of code, then you hit just like in your regular cache. So anyway, so the first thing you do is unload the context, which takes one cycle minimum. Then you travel minimum one cycle again, and then you load the context. If there's nobody running there, you don't have to kick them out. Then it only takes one cycle to unload it into the PC, at which point you can start the instruction cache fetch because you know what the address is. And of course, in the next cycle, you will have the instruction. And then if you're bringing more data, then you need to unload it. For us, the minimum context is basically you need the program counter and you need at least one piece of data, right? Because if you're going there to access memory, well, then you at least need to know what address you're going to access. So the minimum context for us, well, is 2 flits. So altogether, this is 4 cycles, and after 4 cycles, you can basically keep executing at the destination core. And if there is no on-chip congestion, the maximum is 33 cycles, I believe. Of course, if you have congestion both at the core level and on the network, then this can be longer. But still, 30 cycles compared to whatever you can actually do with software support is significant. And so the chip architecture is basically it's a shared distributed data cache, and the data cache is sliced. The addresses it's blocked, and each address range has a cache that will be allowed to cache it. And normally, what you do, sort of by default, if you have to access somebody else's address range, is you send a message to them, all in hardware. You do the load, hardware sends a message and receives a response at word level, and we basically use migration to remove these repeated round trips, and just make it into one trip, and then amortize the cost by making lots of local accesses. So let's talk about a little bit about this decision. How are we going to decide whether you're going to do a remote operation or migration? As you can imagine, this is critical to the performance here. And we have 3 ways to do this in our architecture, in our chip specifically. One of them is instruction-based. So for example, you can say, I want to migrate to core 17, and the thread goes to core 17. This is great for testing, but this is not really useful in practice, maybe unless you have a really fancy compiler. Another way we can do this is triggered by memory operations, that is to say loads or stores. And so you look at the address that you're trying to load or store, and you decide which core you can cache this address. And then the memory instruction itself specifies whether you should do a remote access or migrate. And this is great if you have a very predictable program, or if you have a particularly determined coder who is willing to put a lot of extra effort into this to optimize it. But let's face it, we're lazy, so we also have a way to do this automatically entirely in hardware. So in this scheme, you still migrate on memory instructions, but there's a hardware predictor that decides whether you should migrate or whether you should do this remote access. Basically, it decides whether it thinks it will be worth it to move your thread context over to a different core versus just do a one-off memory access. So how this works is it basically tries to detect long runs of accesses to the same core. So if you have a bunch of accesses to core A, and say you run in core A, and then you have an access to core B, wherever that is, and then you have to go back to core A, then it doesn't make sense to migrate here, right? So you want to do remote access in this case. Whereas if you have lots of accesses to another core, say core C in this case, then you want to migrate and keep running there because you have enough accesses to amortize the cost of migrating the thread. So how do we do this? Well, the answer is we basically count, right? So there's a register that keeps the core ID of the core that is being accessed, whose memory is being accessed, and we count how many consecutive accesses we're making there. And if we exceed a certain threshold, which in our chip is programmable, we insert it into a table. It's kind of like a branch predictor, right? So if you believe a branch is likely, you insert it into a predictor. The next time around, when you come to this instruction, you will look it up in the predictor, and it will be sitting in, this instruction address will be sitting in the predictor, and next time around you will migrate, and every time after that. And the key insight here is that these access patterns are highly correlated to the actual instruction that is being accessed. So if you think about it, if you have a loop, then a given loop probably goes through a given segment of data, contiguous, whereas another loop might have a different stride, and so really it's correlated to the actual instruction we find that you can have. Yes.
One question is that where do you put this kind of for each single core?
Yeah. So each core has an independent.
While your thread is migrating from one core to another, how about the information stored in the predictor?
So that's a very good question. So this table is only kept at the native core, which is where the thread originally started running. And what happens is when the thread goes somewhere, it also counts how long it's going to, how many accesses it did, and it can undo this decision. I will talk about this a little bit later. But basically what we find is that most of the time the thread keeps sitting at its own native core. And it's not worth it to have a separate table on every other core. Right? So, yes.
So let's say you had a loop that would, you have your native thread in core X, and the loop will do 10 X's in A, 10B, 10C. So you migrate over to the core A.
Yep.
And then at the point when you need to migrate to core B, can you just do that, or do you need to go back to its originating core because you don't know?
No, you can just do that.
Do you have guarantees about that the context, the bits of the context that you migrated, will be the same that you need in the next portion of that migration?
That's the
Because
only.
you only migrated the little bit that you thought you needed, right?
Correct. Right. And there you might be mistaken. But so I'll talk a little bit in this piece how we do the migration prediction, right? So basically we adjust the migration context based on how much of how many entries were used after you did the migration, right? So the first time you insert something, an instruction into this table, and label it as migratory, that it's going to migrate next time, you sort of just guess you take half the stack. And when the thread comes back, it tells us why it came back. For example, it might come back because it was kicked out, because some other thread went to compete with it. Or it might come back because it wanted to do a memory instruction on a different core. Or it might come back because it ran out of the context that it was trying to use. Basically, in our case, it tried to pop off a stack and there was nothing left, right? We had to go back to retrieve the rest of the stack. In a register machine, the equivalent is, you access a register that you didn't bring with you. Or it might, there's the reverse case. You might, for example, migrate to a different core and try to get a bunch of data and put it in your stack or fill up your register file, and you might end up not having any more space because you brought too much with you, right, to have space. So memcopy is actually a good example of this, right? So you sort of go somewhere and you load up your context, and you go back. So because the thread reports to the originating core why it came back, we can adjust the number of the context size that we're bringing with us, up and down based on basically how much context was needed on the other side. And the answer to your question your original question is that if you make several of these steps, you still will go back and say, oh, I ran out of stack, right? So next time we will bring more. But program phases change, of course, and it might be the case that even though you had this nice locality over here, you might eventually, this might turn into different addresses, right? And so you'd like to have some kind of mechanism to remove these entries from the table. And this is very, very simple. As I mentioned, the thread coming back reports why it came back, and one of the possible reasons is that it's it didn't make enough accesses, right? So it counts the number of accesses to that core, and if that number of accesses was not exceeded, it will basically report that number, and the next time we will not migrate anymore, right? Because we basically decided that this pattern we detected, this locality pattern, is no longer valid. We're not getting the payoff.
Sorry.
Yes.
If you want to, migrate to a new core, can you make remote access from that core to other cores?
Sure. Yeah.
So you have to, when you decide to go back, you basically have to wait. You have to,
until your accesses have completed.
You have to basically wait until all your accesses are complete.
Right. So we have two ways of doing this. One of them is basically in particular if you do a store. Right? If you do a load,
Yeah.
you have to wait anyway. But if you do a store in particular, we have two kinds of stores. One of them is you basically wait for the acknowledgement, and the other is you basically say, "Oh, forget it, I don't care about the acknowledgement." Right? So actually, if you think about most stores, you don't actually need the acknowledgement. You need the acknowledgement at a much rougher granularity than single instruction. Right? So the similar thing is, as you pointed out, you can't migrate out, right? So we have a third flavor of store, which basically waits for the acknowledgement, but not at the next instruction. It just says generate an acknowledgement, but proceed with your computation. And what happens is you have a counter of how many acknowledgements you're waiting for, and you have to make sure you get all of them back before you can migrate out. Right? So, and there's some kind of instructions that are fences that enforce this kind of you wait for the acknowledgements to come back. You can further. So, yes.
So there are quite a few. I mean, you are doing the migration at sort of kind of core level. So
Yes.
there are quite a lot of other migration system on networking. I think typically people assume there's certain assumption on their workload stationarity. So after you do the migration, you should, the stationarity will ensure you have certain benefits after doing the migration.
Stationarity.
Stationarity means like the workload, for example, might do the network, at the data center network. We also migrate the whole VM to the VM migration, right? So then the assumption here is like after doing the VM migration, it will benefit. It'll get some benefit after that because the traffic, the workload, is going to remain as predicted.
Mm-hmm.
So, is there any such assumption? Do you have any measurement on the stationarity of the workload in your context?
So I'll show some measurements on the examples that we run on the RTL for this chip, and they basically what you're asking is this predictor a good idea, right? Is it doing a good
because
job?
You don't want to have too much oscillation, right? You migrate here, then
Right,
the
that's
workload
right.
move there, and then
That's
so
right.
yeah. So do you have any such assumption or have measurement to back up the assumptions?
Yeah. So in the benchmarks that we have run, so one of them is basically in this case it's the number of instructions that the number of local memory accesses that you're going to do after migrating, right? Because if it's enough, if there are enough local accesses now after migration, then you're good. And because of this hardware implementation, you don't need that many. You need like 4 or something, right? 4 you can amortize. So you don't need to do that. So I had in this slide, I think this slide basically answers your question. If I go back to it, this one. Yeah. So there are some basically, in this case, it's not worth it, right? And our predictor decides that you should just send a message and get, do a one-off access. And only migrate in this region and to the right, where it actually can benefit. The other piece of this equation is that you have to make sure that once you have migrated, excuse this forward animation here. Yeah, so you have to make sure that once you have migrated, that you actually have the opportunity to take advantage of the locality, right? So, for example, you might imagine a case where everybody is competing for, or multiple threads are competing for the same core, and the first one migrates, and another one comes in and doesn't give the first one a chance to proceed, right? So in this case, we have a setting which allows the thread to request basically how many instructions it wants to finish before it can be kicked out, right? So this ensures some kind of efficiency. Yes.
The migration predictor. Is there any fundamental difference between that and a typical prefetch predictor? Because basically it seems that you want to predict what the future sequence of accesses is going to be, which is the job of prefetch predictor.
Correct. So it's fundamentally similar, right? As
so you can basically replace this with any sort of fancy predictor that you may need for whatever.
Exactly right. You're detecting exactly the same thing. You're detecting slightly different things, right? So you're detecting locality more than a predictor. That is to say, a prefetch predictor doesn't really care about maybe the number of how many accesses, right? But it cares about what you're going to access next more, right? Because it can just bring it if it can.
Well, there are spatiotemporal predictors that actually look at the entire sequence.
Yeah.
Both in
So
space and in time. But anyway.
yeah. So
I just
definitely there's a huge overlap here. But yeah, I think the key difference is that you don't necessarily that's basically the anyhow. So I'd like to sort of, while I have still some time, talk about the performance, the evaluation, and a little bit about design complexity. So I'd like to argue that this is much simpler than the alternatives that you can implement in hardware. So specifically, the metric for this is number of BlueSpec rules. And admittedly, I'm kind of biased as co-founder of BlueSpec. But most of this chip is done in BlueSpec. And you can think of these rules, each rule as a unit, as an atomic operation, if you will. Right? So a hardware operation. For example, do an add. Right? That would be a single rule. That operational level. If you are familiar with programming language terminology, it's basically operational semantics level description. And the network on chip router, which is very, very small and simple, it has 9 rules, for example. The management of the stack, you have to move things back and forth in the stack. It's about 8 rules. The remote access is very simple. You send a message, you get a response back. It's 8 rules. The instruction set is most of the complexity. Is for us was 61 rules, and the data cache is about 18. It's kind of complicated, right? It has to think about fetching from memory and serving other people. Instruction cache is a little bit simpler because you don't have to write to the instruction cache. In our case, it's read-only. And in comparison, we implemented a basic MSI protocol, a basic cache coherence protocol, and we found that it was 22 rules for the caches themselves to implement this protocol, including all the transient states, and 11 for directories. And this is for a very simple protocol. And adding migration, it took us 13 rules. So in terms of complexity, we believe it's much simpler than the alternatives. And it is much more simple to verify because the state space doesn't explode as you increase the number of cores, because every address can only be cached in one place. So the state of every piece of data doesn't involve all the possible shares, right, as it would in a cache coherent system. And this is also similar to NUCA, our NUCA at the L2 cache. And people have recognized this in the past, and they have proposed alternative ways of limiting this complexity, among other things, like de novo is an interesting project. Or they have done away with hardware coherence altogether. For example, the Intel single chip computer just doesn't have any coherence, and that's you have to do the software. You have to do all the programming. So for us, there are no indirections or transient states. Basically, what you see is what you get, or what you see is what you have to verify. Everything is local to the tile. There's no sort of global state that you have to keep track of. So verification was pretty simple. Number of bugs. When we did verification, of course, module bugs exceeded the number of bugs in a single tile, but most of our verification for the entire system was done on a four tile system. Basically because simulating a 100 core system just takes forever, and nevertheless we did some of this, and we basically found that there were no bugs in the entire system versus a 4 tile system, which I think is you don't get this guarantee or intuition if you implement something that has cache coherence, right? So that is not to say that there are no bugs in the chip. It's just we haven't found any, right? So there could always be, who knows, right? So what I'd like to argue here is that execution migration provides basically a new point in the design space, right? It's not necessarily better, not necessarily worse. It's just different. It's a different way to implement shared memory. Yes.
So, for example, if you were to have a faster and higher bandwidth interconnect network than the single mesh,
Yeah.
would you still implement the migration?
the migration would benefit more, right? Because I can afford to do faster migrations with less latency if I have more bandwidth.
But it would be still faster to fetch data. You right
That
now you
depends.
have to take
That-
like tens of hops to go around the chip. But if you were to implement it with a butterfly, you can fetch your data in less than 10 seconds.
Well, I can implement the same thing, using with migration. So I would say interconnect is abstracted, and so I don't have the plot here, but we've done studies basically to look how many cycles it takes on average, right? So for example, number of cycles each hop takes in a router and stuff like that, right? And in general, we find that migration benefits more, basically because you can bring more context cheaper. Right? So if you're bringing data in, your main benefit is you're having the amount of flits that it takes to bring in your cache line. But you're not doing anything about this requests and validations and all this indirection through the directory. Right? And so higher bandwidth actually disproportionately benefits migration. Right? So yes.
If I may just comment on it. Sometimes, even if you had zero time to bring data to a certain spot, you just don't want to do things all the way in the same location of the chip for various other reasons, to distribute power density.
Yeah, you could cook it, for
To
example.
distribute heat evenly. So even for those reasons, you may still want to do thread migration in various times. So I guess, even if your data communication was no problem whatsoever, you had that technology, I think you would still want to do thread migration for other reasons. I don't know.
Yeah, no, definitely. It's a yes.
But I would actually now counter this because some of your data are really hot. So if these data are cached on Core 5 will be really hot because all the accesses will go through.
So
We
this,
migrate to
So Core 5 will serve either as the main migration point where all the threads accessing this particular structure will go to, either as thread migration or as remote access. Either way, Core 5 will be the one that will be responsible for the vast majority of the accesses. So you will have a very good distribution of your power and your threads.
You may then, well, I don't want to turn it into my presentation. But I guess there may be other ways to then not do it or kind of control it.
yeah, so this is a good discussion. I think if I can interject sort of two comments. One of them is that the thermal problems are much slower than this, right? So actually, while you can, migration is basically an enabling technology, and this shared memory model is just one possible application of it. Another possible application is if part of your core fails, for example, and your multiplier is broken, and you can keep running on that core until you want to do a multiply. You have to move somewhere else to do your multiply, stuff like that. And it's much more general than, for example, having a special multiply, circuit in this case, because that only allows you to request multiplies as opposed to do any instruction you want, right, with migration. So this is general. Another example is, for example, you have a heterogeneous machine, where you have 1,000 cores, but only 100 of them, or maybe 10 of them, have floating point units, because you don't expect you to be doing floating point very much, and so you just do the migration and do your floating point wherever you want, right? So, how many applications? Of course, you can do power-sensitive migration as well. Although temperature rises pretty slowly, so you can sort of respond to that without the need for this.
Not that such fine granularity.
Yeah, because it's basically slow compared to how many cycles, right? It takes a while for the stuff to heat up and cool down and stuff, right? So what you were saying about the Core 5 being hot, you have the same problem one way or the other because your L2 is probably hosting that data anyway, right, on that core. And you have to do the fetches from the L2 and you're burning SRAM.
I mean, if you go the traditional way, but maybe we should take this offline in the
Okay,
interest of time.
yeah.
But
So maybe,
yeah.
but this is basically ways around it, right? You can trade off migration versus remote access, and they have different power costs, right? Remote access is cheaper, for example, right? So you can take this into account. but because this is a long-term effect, you have time to sort of decide what you're going to do about it and configure the hardware. So yeah, so I'd like to present some results actually before I run out of time completely. So the performance baseline, what we did was we implemented a cache coherent equivalent to our chip in RTL, so it's synthesizable hardware. Bless you. We idealized it in two ways. Basically because we didn't want to implement a specific, cache coherence protocol and then have somebody say, oh, if you just implemented this slightly more complicated one, it would all do really better, right? So we basically don't charge the cache coherence design for anything related to invalidates, right? So if it has to invalidate a cache line, it's instant. It just happens, which is a big benefit for coherence. Also, the last level cache, in our case L2 performance, is idealized, and so when you fetch, it only costs you net delay, and this also benefits cache coherence because they tend to do more L2 fetches than we do. So this is strictly better than any directory-based implementation that people have proposed, certainly that I can imagine. And our simulations are in RTL, basically because our architecture is so different from other that to be really, really credible, you need to model everything at cycle accurate level. And we held all this RTL for the chip already, so it was natural to compare it. Disadvantage is that it's very slow, so the benchmarks by necessity that I'm presenting are very small. On the other hand, it's uncompromising. There's no argument that is actually what is happening, right, in the hardware. So how much does this cost in terms of area? Well, we have this extra core context that I mentioned. We have some extra routers that we can do away with actually, but we just put them in the chip because it's just tiny. And this migration predictor, which is tiny compared to the rest of the core. So this is the area of the core in square microns, and the predictor, the blue thing over here, is tiny compared to everything. You can see that the actual memories take up the most of the area in the tile. On the other hand, we save a lot because we don't have to have a directory. So we had 100% and 50% directory just for comparison. And I'm not going to argue that it's necessarily it's 5% better or 3% better or 10% worse, whatever. I think the message here is that it's on the same order of magnitude in terms of area as a traditional implementation. You lose some, you gain some, but it's on the same order of area. And of course the leakage power, which is all we show here, is related to the area, right? And dynamic power is related to the traffic, and so this is what we decided to measure. Another way to measure this is basically to do very low-level simulations with an RC model, and it's just crazy. It would just take forever. So we just decided to replace the actual dynamic energy numbers with on-chip traffic as an approximation, because everything else is the same, right? So in terms of completion time for this set of benchmarks, all of which were basically either compiled using our compiler for our special architecture and then hand optimized, or just written in assembly. This black bar you can sort of ignore maybe, because there's remote access only without any migrations. And we always do better than that because we either choose this or we migrate, right? So this is kind of clubbing baby seals, I guess. I guess we could do worse than this if our predictor was really bad, but we don't. So the real thing to compare to is this cache coherence, this idealized cache coherence model, and we tend to do better. In one case that I will talk a little bit more about, we do worse, and that brings up basically what you suggested earlier. So in terms of network traffic, we do strictly better. For some applications that are particularly suited to this architecture, we do amazingly better. This is, I think, I don't know, 40x less traffic or something like that, something ridiculous.
What is this application doing?
This is parallel cross-validation. So it's basically, it's training a perceptron, and it's doing parallel cross-validation, right? So it's choosing one part of the data to be the training set, and the other to be evaluation set, right? So it trains the data, trains the perceptron on a subset, and then cross-validates on the other part. And basically what people do, I'm not a machine learning person, but what I understand, what I'm told people do, is they do cross-validation, so they choose the subsets to be different, right? And the key feature here is that you're using this data in all these threads at the same time. So if you can keep all of this data on chip, as much of it as you can, then you win hugely, right? And also, these threads are not necessarily using the same data at the same time, right? So there's a kind of a pipelining effect, which brings this makes it a very, very nice application for us. So yeah, so also note that for cache coherence, we don't include invalidated traffic. So a real implementation would actually do worse. Yes.
So was there anything about the memory access, number of memory accesses?
Number of
Or
memory
cache
accesses was the
coherency?
same.
Yeah, off-chip memory accesses.
So we chose these benchmarks actually to fit in the cache,
So
and
it
we
does
did
fit
model.
in the cache, I see.
So these benchmarks fit in the cache. So we were specifically interested in an apples to apples comparison, right? So we specifically chose to compare something that fits in the cache. In a realistic system, you have a much larger L2 cache, right? And yeah, in cache coherence, you will have more memory access, but we didn't charge them for that effectively, right? So, yeah. So how does the migration system work? Well, the average migration latency, as you can see here, tends to be pretty low. Amusingly, it's really high for this benchmark on which we do really well. But the reason is that this number also includes the amount of time that a thread spends waiting at the core to be migrated in, right? So in this case, there's this pipelining effect that I mentioned earlier. That basically a core works on its piece of data and moves to the next sort of, I don't know, slice of data, next piece of data. And if the previous thread isn't done, it basically has to wait until the previous thread completes, right? So, and this is included in these numbers. The other thing I'd like to point out is that the average size of migration actually varies quite a bit, right? So it was important for us to do this partial migration. It validates that choice.
What about the average hop count?
The average hop count.
Like how spread out are these in terms of access to each other's space?
So this is highly benchmark dependent. I don't have a plot for this, but there are some that basically. So for example, Jacobi is just matrix, effectively matrix computation, right? And it tends to access its own region of matrix and then do some accesses to neighbor cores. Whereas parallel cross validation, for example, goes all over the chip, and we actually do better in that case compared to traditional solutions. Because we can leverage this, effectively, if you don't do replication, then you can put more data on the chip, and that's much cheaper to access than going off chip, in any case. So and we can benefit from this. So finally, the keeping the migration rates low using this predictor has been key for us, and you can see that basically, if for all these benchmarks, they're pretty low. So memcopy, you can imagine what you do is you go to a different core, you migrate, you load up your context, you bring it back, you store it, and you keep doing this sort of, doing the shuttle runs. And so it's easy to sort of figure out how much of this, what these migration rates are at a maximum, if you will. In most of these, they're fairly small. In this case, this last benchmark we didn't do very well on, and this is because of what Nikos mentioned and I described briefly. Basically, all these threads are getting evicted, right? So what's happening is, because this is a benchmark which does a random table scan, right? So it's sort of simulates a SQL read access, right? So you search for a key in a particular chunk of data. So we randomly pick the chunk of data that we're going to search, and we just keep doing this in a loop in each thread. And so because of effectively the birthday paradox effect, what you get is you often get some cores that people are ganging up on, right? And what happens is we, this contention, and core comes in, kicks the other guy out, but the other guy isn't finished yet, and so forth, right? So, it's different from this case, because in this case it's sort of a very structured pipeline benchmark, right? So one thing you can do in here is you can improve this. We've done some studies that we basically are able to improve this number by careful scheduling of requesting of how many accesses I want to do, right? But it's not necessarily obvious in all cases. So I think this is a good example for sort of the worst case that for our system. So summary of this work. The performance we think is comparable, depending on the benchmarks, better, worse, whatever, to state of the art. But at the same time, it's much simpler to implement. In fact, if I want to scale this to 1,000 cores, the only two things I have to change is the number of bits we use to represent the core, and the mapping between the address and the core. We basically just take the top 7 bits or whatever. And provided we change those two things, we can basically just place however many cores on the chip we want. There are some challenges. Data placement is the obvious one. But I also mentioned that some workloads, like the last one that I showed, require some orchestration to avoid bad congestion. On the other hand, those opportunities I mentioned, I sort of view this migration as an enabling technology, right? You can implement stuff on it. And really, I sort of feel like this memory, unified memory system is sort of a good test case for it that really stresses out this migration hardware. Anyway, so what I think are the things that I would like to do in the future, of open questions, directions. I think shared memory needs to be really locality sensitive, right? So as we saw, that if you have the best strategy, whether it's cache coherence or whatever, or migration or remote access, then you get a big payoff. But it is very highly dependent on the workload and maybe the actual program phase. So I think we need to basically have a system that is able to respond at runtime to the application patterns, right? It's basically adapt to how the application is behaving. And the key here is that the hardware has to do all the tracking, because the tracking has to be so fine-grained, sort of memory access level, right? And I think that you can do the actual adaptation, switching to a different scheme in software, because you can take your time. Another thing I'd like to do is, more generally, start moving mechanisms that have previously been in software into the hardware. So this work that I've presented is an example of this, right? We've taken this thread migration, which is normally a software thing, and we've implemented it in hardware. There are, and the reason it works, incidentally, I think, is because once you get to 100 cores, about that level, the trade-offs become different, right? Because the on-chip distances become longer, effectively, in terms of number of hops. And so things that work, for example, for 4 cores or 16 cores, you can even have a bus maybe, that works really well. But if you have a really large number of chips, number of cores, it doesn't really scale. So I think 100 plus cores, maybe 1,000 cores, is an opportunity, if you will, to do some innovation, because the trade-offs are different than in the past. So things like memory management, for example, I think some pieces of this you can move into hardware. And I think a success story for this actually is the GPGPUs, right? Because this is exactly what they did. They redefined the boundary between how you write the software and and what the hardware does. And if you're willing to live with that, then you can get really, really huge improvements. And I think we also need to sort of globally, as a community, we need to rethink how we're going to do parallel programming, because we can build the hardware, we don't know what to do with it basically. Right? We're building faster and faster machines to run C, and C is not the best sort of language, if you will, for expressing parallelism. Right? So I think the real solution involves both hardware mechanisms and software mechanisms, that is, program methodology and so on. It's sort of a long-term thought, of course, right? But an encouraging direction in this, for example, is Intel has done some work in the new course to make it easy to do transaction memory, for example, right? So it's not like I'm completely, so anyway, so yeah, I don't know if you have any questions. Thank you.
Yeah, I have a question. So, to my understanding, data migration is also necessary for load balancing, right?
Both data and thread migration.
No, data migration is necessary for load balancing, especially dynamic load balancing.
Mm-hmm.
Right. So in your system, if you don't actually allow data migration, you only migrate threads, then the data partitioning or data placement is very, very critical, very important. But to my understanding, there must be some applications where you do need a dynamic load balancing to actually achieve better performance. So in that kind of, for those applications, how are you going to actually handle, improve the performance?
So the work I described
Mm-hmm.
in the chip, I mentioned it doesn't have virtual memory, right?
Mm-hmm.
It does not have virtual addressing. In a real system you might sell or buy or whatever, right? You will actually have virtual memory. And this provides you with an opportunity to add indirection, right? And because you have the virtual address that you're using to address, but where the physical address is stored, you can move.
Yeah.
You can use that sort of address translation as a level of indirection and do the data movement, right? So, for example, you might learn that not just for load balancing, but you might also learn that that I don't know, your application was using this data, and in a given thread, but another thread is currently using it, and you'd really like these combinations of pieces to be in a different place in memory, right? So you can use this virtual address translation to do that. I think at a lower granularity than page level currently, but I haven't specifically looked at
Okay, so yeah, I think a follow-up question is actually, if you have such a kind of like mechanism there, will that actually kind of change the way you actually handle thread migration, or will that actually decrease the benefit of thread migration?
I don't think so. I think it will add opportunities because of this address translation, right? That you can move things under the covers, as it were. There are obvious things that some people have mentioned already. The TLB, right? Do you move the TLB or not?
Mm-hmm.
And I think the answer is no. But maybe you want to take a piece of the TLB, just not a big problem. It's a trade-off between taking some of the TLB with you or making the TLB slightly larger, or maybe not even at all. It's the same thing with data cache, right? And another piece that we did not address here, because this is a bare metal chip, there's no operating system, is how does this interact with the operating system, right? Because the key here, the key to the performance, is that all of the migration is done at hardware level, and it does not involve software. So somehow the software has to know where the thread is running, right? So, for example, a very sort of rough way of ensuring this is make sure you every so often, maybe every few thousand instructions, every million instructions, come back to your native core and check with the operating system if it wants to reschedule it or something, right? So that kind of thing. So I think the operating system doesn't necessarily need to know where everything is running, but every so often it needs to be able to communicate, right, with the thread effectively. So yes. Go ahead.
You briefly mentioned something in your talk that goes back to fault tolerance. So you could have a core that maybe a piece of it goes off, has a hardware or something, like multiplier, you mentioned the example, multi-point multiplier. Now this technology allows you to keep on using this code, not take it offline completely, and ship off computations that use this particular now faulty hardware unit somewhere else. And I think this gives lots of brownie points to an architecture like this. So what I would like to see is, can you comment on what types of extensions you would need to support fault tolerance in that manner?
So I believe there was a paper that suggested this kind of thing. It's called core salvaging. And they basically said that, you know, pretty much what I suggested, right? If your whatever the execution unit X is broken, then you just migrate somewhere else. But they sort of assumed. Actually, there have been a number of papers that have assumed that it's possible to quickly migrate among different cores, but nobody has actually shown how to do this. The closest that people have come is actually a very clever way of you can use the cache coherence system to sort of do this movement to an extent. But yeah, but I think for obviously you need to detect when your FPU or multiplier or whatever is broken, right? So depending on if you have if you might have some hardware that's cheaper than the actual multiplier to check on the multiplier, or have some other ways of detecting when it goes wrong, right? So that's one component. And I think as long as you lock out the multiplier, then it basically you don't need to do anything else, right? Because you only need to know that every time you see a multiply, you need to move to, right? You need to some kind of.
So then the only thing missing is the hardware that has the monitoring.
Hardware that has the monitoring and some kind of storage that tells you, for example, some bit vector that says, oh, this is broken. When you see an instruction that's going to access this, move it somewhere else.
But everything else is already in place.
Correct. So another interesting question here is that we haven't addressed in depth in my dissertation work is where are you going to move, right? It's not necessarily with this memory system, it's obvious, right? Because there's a unique place. But if you're going to do something more complicated for thermal or for fault tolerance, you might like some kind of idea of which cores are busy, where there's where space is and stuff like that. So that requires some. Yes.
So throughout your talk, I think we kind of get the feel that migration policy on a lot of things, right? Especially application by application. But what you've done is you've taken thread migration, both the mechanism and the policy, you subbed that into hardware. Why the policy? Right. So why not architect an interface to the policies, right? So for OS programs, why can't they say, or why shouldn't I be able to say, migrate after 3 subsequent accesses to the same location or whatever? Just one simple knob like that.
So actually, this specific knob we have in the hardware. You can say
Okay.
you can set the threshold and stuff like that, right? So and on a per core, per predictor, but per core, the same thing.
Did you
But-
measure that?
So we found that 4 was basically the best. It has to do with more with how much you can amortize by moving the threads than by what application you're running, right? So 4 for us turned out to give the best results. That is not to say that this is the case for all applications. It also depends on what access patterns are, right? For example, if you always access data on the other side of the chip, then maybe you need more info. But yeah, I think there's a big open sort of question that you're asking is what role does the OS play in changing this? And yeah, you can add a whole bunch of knobs that allow the OS to adjust where you're going to migrate to, how often you're going to migrate, to for example solve this problem that I show with this guy at the end, right? One way.
Sorry, a lot of people are waiting anxiously
Yeah,
to
I'm sorry.
take out for lunch, so let's wrap up.
Okay.
with a quick-
Yeah, we can take it offline if we.
Okay.
Yeah. Thank you.